You feeling better after already?
I'm not running fever. I haven't ran fever for 24 hours.
Hey, God is a step in the right direction.
Otherwise, I wouldn't be here. I'm not gonna take a chance on passing off whatever it was. I think it was just pure exhaustion hit me, and my husband had a sinus infection the week before. I think he gave it to me.
How rude.
I know.
You have tuition.
Thankfully, the classroom's a smaller classroom to teach in today, so I don't have to raise my voice. We're gonna go as long as my body can handle it without me starting to cough too much. You sound like me.
Okay.
We'll do this. One day at a time.
Bill,
I'm here.
a little better.
Okay, folks. Um, So today what we're going to be doing is what I was originally going to teach yesterday, plus a little bit of what I was going to teach today. I'm gonna have to really figure out the schedule. I do want to give you a little bit of an overview of where I think things are going to head to this week, and I do plan to update the Blackboard. First of all, if all goes well, I'm going to go over I will go over integrated rate laws today. I also hope to go over collision theory, energy of activation diagrams, and catalysts today. Then on tomorrow in class, my goal is to go over reaction mechanisms. What that will mean is on Friday, I won't be here on Friday. Dr. Yang is going to be taking the class on Friday. He is going to introduce the concept of equilibrium. So that will be the focus for Friday's lecture. As far as your tests are concerned, I am in the process of grading them. I've got about 3 pages down of everybody's test because I grade it page by page so that I'm consistent for the entire class. I don't know anybody's grade until the very end. My goal, I don't see it being done by tomorrow, but we'll just see how today goes. My goal is that I can have the grades entered by Friday and then the test passed back on Monday. Normally I would already have them back to you, but well, circumstances didn't allow for that. So I didn't get things graded like I planned. Normally 1 week is my limit on an exam. This time it may be a weekend, but normally 1 week is my limit on an exam because I know exam grades, they're high dollar grades and people are more worried about those. Speaking of the exam, I know it was long in the fact that if you did not know what you were doing, you probably did not have time to complete it. But was there anything on the exam that was unexpected? That's what I try not to do, is throw you curveballs. I can't promise that the exam's not going to be hard. I can't promise that the exam's not going to be long, but I can promise you not to throw you curveballs. And so if you did the optional homework, usually you know what to expect on my exams. And that's all I can promise you to do, is be upfront and with an exam. Any questions before I get started on kind of the overview for the week or anything else? I'm not going to talk loud today. If you can't hear me, let me know. But I'm going to actually shut the door so that we don't have the outside influence. And I'm mainly shutting the door because I don't want to have to speak too loud because I'm afraid I'll start coughing if I do. So, okay. So before the exam, we had gotten into chapter 14 of the textbook, which deals with kinetics. Kinetics discusses the speed of a reaction. We talked about the rate of the reaction, and we can describe the rate of the reaction as the negative change in concentration of the reactants versus a change in time. Or we can describe the rate of the reaction in terms of the formation of a change in the products versus a change in time. In other words, basically your rate of the reaction is kind of like a speed. Well, it is a speed. It's kind of like when you think of your speedometer, how many miles you go over, how long it takes you. So if you're going 60 miles per hour, you'd be doing 60 miles in 1 hour. The rate, that's all the rate of reaction is. It describes how fast the reaction occurs, but it doesn't according to the disappearance of the reactants or the formation of the products. And as mentioned before, signs in chemistry typically are talking about what's happening to the material. It's not talking about, because you can't have a negative concentration. You can't have a negative speed. The minimum you can do is 0. So it's, the signs are representing which direction it is moving. Is it, are we losing something or are we gaining it? So we talked about the rate of the reaction. After we talked about the rate of the reaction, we then talked about the fact that the only way to really determine these speeds of the reaction is through experimentation. And through experimentation, we can develop a rate law where the rate is equal to the rate constant times reactant 1 raised to some order times reactant 2 raised to some order. And the only way to figure out those orders is through the experimentation. There are a couple of different methods that we use. The first method is the one that we talked about prior to the exam, which is the method of initial rates, where you run a series of experiments and you have a starting concentration of reactant 1, a starting concentration of reactant 2, determine the rate. You run a second experiment with a new set of concentrations. And ultimately what you do is to perform the calculation, you have to hold one of the reactants constant while changing the other reactant in order to understand how the reactant you did not hold constant impacts the speed of the reaction. So the method of initial rates it's very useful. You will be using it next week in lab to determine the order with respect to the bleach. Yes. But the other way is what we're going to talk about today. Which are integrated rate laws. Okay. With integrated rate laws, you collect a series of data over a set of time. So for example, we might have time in seconds, and we collect and we talk about the concentration of A in molarity. And so if at 0 seconds, you have a 10 molar solution, then we pay attention after 10 seconds, it's down to 7.94. After 20 seconds, it's down to 6.30. This is simply data that we would be collecting. 5.00 after 30 seconds. 40 seconds is 3.97. 50 seconds is 3.15. And then 60 seconds, 2.50. So all we do when we're dealing with an integrated rate law is we're going to collect a series of data. What is the concentration of our reactant after so many seconds during the reaction? With this data, we then graph the data. And we developed 3 graphs. And actually, we did this back at the beginning of the semester when we talked about graphing. That's what we were doing, is the integrated rate laws. We graphed 3 sets of data. You graph the concentration of A versus time. You graph the natural log of A versus time. And you graph 1 over A versus time. Or in other words, the inverse of concentration versus time. Now, whichever of these graphs produces the best R squared for a linear line it is indicating the order with respect to reactant A in this case. So in other words, it's telling you what the exponent is. So going back up to these graphs, for example, basically what this is saying is if you were to get, if the concentration of A versus time gives the best straight line or best R squared, then the order of A is 0. So in our little rate law, it would be rate is equal to K times A to the 0 order. If the natural log of A versus time gives the best R squared, then the order of A is 1. So we would have rate is equal to K times A to the power of 1. If the last one, 1 over A, gives the best R squared, then the order of A is 2. So in other words, we would have a second order reaction with respect to A. Now, one thing we haven't discussed that let's discuss at this point is what do these orders mean with respect to the reaction speed? Well, you don't have to memorize this. You can figure it out mathematically. If I have, let's say I have a concentration of A equal to 0.1, and it is 0th order. Well, that would mean that what we have in our rate law is rate is equal to K times 0.1 raised to the 0. Well, when you have a number raised to 0, what is it? It's 1. Anything raised to the 0 power is 1. So in other words, this comes out to be rate is equal to K. If I have A equal to 0.2 and it's 0th order, rate equals K times 0.2 to the 0 order. What is 0.2 raised to the 0? It's still 1. So in other words, rate is equal to K. So what it means is if we have a 0th order, the concentration does not impact the speed of the reaction. So that's something to keep in mind. Let's talk about first order. Let's say we have A of, and let's make it life easy, 1 molar in its first order. So rate equals K times 1 raised to the 1. what is anything raised to the first power? Itself. So in this case, it would be rate comes out to be equal to K. But let's double that and make it 2 molar, and it's still first order. Now rate is equal to K times 2 to the first power. What is it? Anything raised to the first power? Itself. So this is rate is equal to 2K. So in other words, I double the concentration, or basically whatever I do to the concentration, you do to the speed. Of the reaction. So if I were to quadruple the concentration, I'd expect to quadruple the speed of the reaction. So that's what it means when we say something is first order. It means that it has a direct impact on the speed of the reaction. Whatever you do, it is a direct correlation. Questions? So this is the next thing for first order. And we can do the same thing for second order. If we have A of 1 molar and it is second order, rate equals K times 1 squared, which in this case means rate is equal to K. But if we double the concentration, 2 molar, and it's second order, then rate equals K times 2 squared, or in other words, rate is equal to 4K. So you can see the correlate, the cause and effect that changing concentration has. So even if you don't want to memorize what it does, you can figure it out simply by putting in a value and calculating. In this case, doubling the concentration for a second order quadrupled the reaction speed. Okay, let's go. So we were figuring out first order and second order and so on and so forth using graphing. Let's go back, and I kind of segued off a little bit into a tangent so that hopefully you understand what we are talking about when we talk about orders now. Order directly impacts the speed of the reaction. You can figure it out mathematically if you need to, because that, to me, it didn't make sense until I figured it out mathematically, and then I'm going, oh, yeah, that makes sense now, because 2 squared is 4. But originally it was like, what? That's a lot of memory. But there is something to it. But let's get back to the integrated rate laws. In the flipped classroom, I actually derived these integrated rate laws for you. But here, I am just going to give you the integrated rate laws. So, and I'm gonna try, it's gonna be small, and I apologize for that. So we know if it's 0th order, the graph that we want is going to be concentration versus time. The integrated rate law is going to be the concentration of A at a given time is equal to a negative K times time plus natural law, or plus the concentration of the original solution. I'm gonna put all of this up here and then I'll come back and define it. The units of K is going to be molar per second. And the half-life can be calculated as T1/2 is equal to A naught over 2K. Like I said, I'm going to come back and I'll define all of the variables here in a few minutes. Let's just get this table down, because you're going to want to refer to this table when you're doing the problems and stuff of that nature. First order, the graph we're looking for is the natural log of A versus time. The integrated rate law is the natural log of A at a given time is equal to negative KT plus the natural log of the original concentration. The unit for K is per second. And the half-life is T1/2 is equal to 0.693 over K. Finally, your second order, and we're not going to talk about odd orders. We're going to keep it down to the 0, first, and second, folks, is 1 over A versus time. The integrated rate law is 1 over A at any given time is equal to a positive KT plus 1 over A naught. The units for the rate constant is per molar second. And the half-life for a second order reaction is 1 over K times A naught. So just to define the variables, A sub T is concentration at a given time. K is still the same. It is your rate constant. T is time. A naught is your original concentration. And T1/2 is the time it takes for 1/2 of the concentration to disappear. Yes. The answer to your question is no and yes. Yes and no. I give you all of the equations, but I don't necessarily have them in a tabular format or even in a 0 first, second order organization. They're just there. So you have to know what to look for. So I'm going to actually help you hopefully know what to look for. So I'm going to go back up to this table now, and I wanted to, first of all, the graph is where I start. And we're going to do some problems here in a few minutes. I know it's taking me a long time to build up to the problems today. But the graph is where I start. You'll notice that this is just regular concentration. This is just regular concentration. This has concentration in the numerator. This has concentration in the numerator. Compare that one to the second order where the concentration is in the denominator. This is concentration in the denominator. This is concentration in the denominator. First order is the oddball because we deal with natural log. And you'll notice that it deals with the natural log. And the half-life is an oddball. It doesn't have concentration at all. So those are ways that you can know which one to recognize. If you pay attention, the graph is the key. The graph holds a lot of information. Not only does it hold information about which sets of equations to use, but it also holds information as far as the rate constant, and so many other things, because these equations, these integrated rate laws, they have the form of y equals mx plus b. Y equals mx plus b. Y equals mx plus b. And so what you'll note is that your slope is equal to a negative rate constant for zero order. Your slope is equal to a negative rate constant for your first order. But for your second order, the slope is equal to the rate constant, a positive rate constant. And that's why I specifically highlighted whether it was positive or negative. That looks like a T. You will notice that your y-intercept should be equal to your original concentration. Or in the case of your y-intercept, in the case of first order, is equal to the natural log of your original concentration. Finally, your second order y-intercept is equal to the inverse of your original concentration. So there's a lot of information that's embedded in that y equals mx plus b. So when I ask you to draw the graph, when I'm asking you to give me the equation and the r squared value, the r squared value is telling us which graph to use. So it's telling us the order with respect to that particular component. The linear equation has information embedded in it as to what is your rate constant for this reaction. It has other things embedded in it. Questions? Let's take a 10-minute break. Give me a little bit of a break so my brain can function again, and then we're going to do some problems so you can see how to use this stuff. Column D up there is going to be 1 over the concentration. And I graphed each one. So this first one is concentration versus time. And I would add a trend line. And I always get my r squared in my equation on the table. And it has an r squared of 0.9624. The next one was the natural log of concentration versus time. Add a trend line. Set your r squared. And it has an r squared of 1. And then the last one was the 1 over the concentration versus time. You add your trend line. And it had an R squared of 0.9623. Of the data, the one that had the R squared closest to 1, the best R squared, the best line, was the natural log. So what this tells me from the graph is that natural log of concentration versus time is the best straight line. So it's first order with respect to A. So I could write the rate law is going to be the rate constant times A raised to the power of 1. That's all from which line gave this, which graph gave the best straight line. When we looked at the linear, it's all about linear. We're not worried about exponential functions or anything like that. It's all about the linear.
So this only applies to this set of numbers, right? It'll be different to different set of numbers.
This only applies to this set of numbers that we started with. Now, when I got my equation, y equals negative 0.0231x plus 2.3027. This has your formula of y equals mx plus b. Which, because it is the integrated rate law for the natural log, that means that the equation is the natural log of A at a given time is equal to negative KT plus the natural log of A naught. So you can to get your rate constant, if you look here, slope, the negative slope equals the negative K. So negative 0.0231 equals a negative K. So K, which is your rate constant, has to be equal to 0.0231, and it's per second because it is first order. Your y-intercept what this is saying is 2.3027 is equal to the natural log of A naught. To take and get both sides, that means E of 2.3027 equals E of the natural log of A naught. that cancels out that, and therefore a naught is e to the 2.3027. Which should be 10, if I'm not mistaken. Yep, 10. Which actually matches up with what we said it was to begin with. Yes,
Where did the concentration at a certain time go?
it hasn't gone anywhere yet.
Like when you solved that, you moved K over to the left side, right?
No, I didn't. I'm using the fact that I'm just using the equation. So the slope, when I did the rate constant, the slope is the rate constant. B is natural log of A naught. So I haven't done anything with the A sub t because I'm just taking out the piece of the equation at a time. Now we can do something with AT.
So what did you solve for here? You solved for A.
I solved for A naught, the original concentration, which we knew.
Isn't it 2.3027?
No, the natural log of the original concentration is 2.3027.
Gotcha.
So you have to actually do the math to get it back to A naught, which, like I said, in this particular case, if you go back up to the original, we knew it. But if you don't know it, you can calculate it. Okay,
I have one more question.
yes.
How did you just set that equal to the lateral log of A naught?
Because it automatically is, because B is 2.3027. B is
Oh, okay.
natural log
I see
of
what
A
you're
naught.
Yeah.
They're the same thing.
I got you.
One's just the value instead of the formula. Now, since we know this is first order and we know, now we can also calculate T1/2. That's going to be 0.693 divided by K, which was, so 0.693 divided by 0.0231 is going to be equal to our half-life. Which is 30. Which, to be quite honest, again, in this particular case, we knew because half, what does half-life mean? It is when does half of the concentration, or when has half of the concentration disappeared? If we started out with 10 molar, then half the concentration is gone when it's down to 5 molar. And that happened at 30 seconds. This one, I liked this one simply because you can prove your math correct. So that you can see it does work. I'll be doing one here in a little bit where you can't prove your math correct because you can't just look at your table and get your answer. You have to actually do the math, but I want you to see how the math does work. We can ask the question, what will be the concentration after 135 seconds. Now we can't get into this. It's not there. All we know is it's gonna be less than 2.5, but we have no clue what it's gonna be. But that's where this equation again comes into play, because you know the log of the concentration at a given time. So in other words, our log of our concentration at 135 seconds is going to equal a negative 0.0231 times T plus 2.3027. And we know that because y is equal to our natural log of concentration at a given time. Our time is our x value. So we go through here. The natural log of our concentration after 135 seconds is equal to a negative 0.0231 times 135 seconds plus 2.3027. So the natural log of A at 135 seconds is equal to a negative 0.8158. You take the E of both sides. Whoops, added a 0. And you get, you'll get A at 135 seconds is equal to 0.44 molar. Which, okay, again, I don't know what it's gonna be, but I mean, we were down to 2.5, so I'd expect it to be below it at least, and it is. Let's look at another example. So I've done the same thing with the next example. And I'm going to, I'll get the graph started, but I want you to answer the following questions. So the questions you're going to answer include okay. So I have this graph. Lines. The first one has a R squared of 8685. The second one has an R squared of 0.9665. And the last one has an R squared of 0.9999. So what is the order with respect to A? Second, because that's your best R squared. So I'll give you the equation now so that you can maybe read it a little easier. Okay, let's look at how it's going. We determined it was second order with respect to A because the one over the concentration versus time is the one that gave us the best straight line. The rate constant for the reaction, well, if you look at your equation for the integrated rate law, the natural log of A, and I'm sorry, wrong one. 1 over A at a given time is equal to a positive KT plus 1 over A naught. So our rate constant was the slope. So 0.0614 is equal to K. So that would be 0.0614 per molar second, because that is the unit of the rate constant for a second order reaction. For the next equation, you had T1/2 is equal to 1 over K times A naught. You know K because we just figured that out. That was 1 over the 0, or it's 0.0614. But you need A naught. That's where you would have had to have calculated this piece to get to A naught. Because 1 over A naught is equal to 99.283. Therefore, A naught is equal to 1 divided by 99.283, or A naught comes out to be equal to 0.01, I think it was. Yeah, 0.01. And so when you calculated this out, you would have gotten an answer of 1628 point something 6. So I rounded it to 1629 seconds. Yes.
If I did instead of 0.01, it was I did the whole number and I got 16, 17. Did you get much better?
Yes, as long as I can see how we differed. And then what is the concentration of A after 2200 seconds? Basically, for that one, you were solving 1 over AT. So the equation for that is 1 over AT is equal to 0.0614 times 2200 seconds plus 99.283. And you solve for AT, and that gives you 0.0043 molar. Questions? Basically, folks, it's understanding what y equals mx plus b means to a large extent. Once you've identified the order with respect to that particular substance, it's then knowing what y equals mx plus b means.
How would this question look on a test if we don't have
You'll be given the graphs. You'll be given the equations, R squareds. So it looks a lot like it did here, except in the fact that I gave you the graphs. I mean, I also state what everything means so that it's not without labels. It has labels. Questions? So integrated rate laws, you'll be using the integrated rate law when you get into lab next week. One of our substances is a blue dye, and the blue dye fades in the presence of bleach. And so we're going to watch the absorbance of the blue dye disappear over time. And so that's going to be going to allow us to determine the integrated, the order with respect to the blue dye is by using integrated rate laws. Questions? Okay. And I did do a few of these problems for you in the homework, in the optional homework. I included my graphs in those optional homework so you can see where I got the data from. And yes, the test looks very similar. Okay. Okay, so now what we've done is we've talked about rates of reactions in general. You can just study the speed of a reaction by analyzing one component at a time. What does it do to the reactant? What does it do to the product? We've talked about how to determine the rate law. The rate law always has a generic formula. Rate is equal to K times the concentration of the reactants raised to their order. And we have found two ways to determine those orders. One is the method of initial rates, and the other one is the integrated rate law. Now what we're going to do is we're going to talk about collision theory, energy of activation, and things basically that propel the reaction forward. So we know how to come up with the rate law. We know what it means now with when I say something is first order, what does that mean regarding if I alter the concentration, what's it going to do to the reaction? Well, it's going to simply, whatever I do to the concentration, I do to the reaction, right? And we know that the rate law does not necessarily reflect the stoichiometry of the reaction. And we've discussed the collision theory to some degree, but today we're actually going to discuss it officially. We're going to talk about the energetics of the reaction. Because it's energy that drives the reaction. Okay. The first thing is collision theory. Let's take all the desks out of here. And let's plan to only have two, this is all theory. And we're only going to have two students in here moving around. What's the likelihood of those two students, those two individuals, running into one another? Not super likely. Now, let's put, even with, without all the desks in here, let's put you all back in here. What's the likelihood of you colliding with somebody? That's collision theory. So one thing we can say is that if we increase concentration, we should increase the collisions. Does that mean a reaction is going to occur? No. Just because there's a collision doesn't mean that a reaction is going to occur. In order for a reaction to occur, there has to be more to the collision. The molecules have to collide with the correct orientation for there to be something that occurs. If we want to take nitrogen monoxide, for instance, and ultimately make NO2, we can't have this collision because that's not going to give us the correct orientation. We can't have this collision because that's not going to give us the correct orientation. The only way we're going to get to that NO2 is if we get the correct collision so that we can start to get that NO2. So just because we increase the number of the concentration does not mean it will increase the collisions. Increased collisions should, in theory, increase the chance that you get collisions with the correct orientation. Because the more you collide, the more likely you are to react at some point. But there is still one more factor. And this is the fact that energy has to drive this. So energetics. If I have this process and it has an extremely high energy of activation, the likelihood that the reaction is going to occur becomes next to negligible again. So I could increase the concentration, which is going to increase the collisions. But if I don't do something about the energy in this particular example, then I'm not going to have a reaction. So so basically there's multiple factors that must come into play in order for a reaction to occur. You have to have the collision. So increasing the concentration is a good idea in general, because it promotes collisions. You have to have the collision with the correct orientation. The molecules have to collide with the correct orientation. And they have to collide with the correct energy. The energy of activation diagram can tell us a lot about whether a reaction will occur or not. And it's all based off of that energy of activation. And right now I am seeing a lot of dead faces and I'm not feeling very perky, and I've still got another one of these. So I think I'm going to have to pick up with energy of activation tomorrow in class, and then let Dr. Yang, instead of doing equilibrium, he's going to have to do reaction mechanisms with you. Yes.
How do you get any way to orientation?
You don't have any way to control orientation, except, again, if you increase the concentration, you're more likely to increase the fact that they're going to collide with the correct orientation. And as far as this energy of activation, we're going to increase the likelihood on most accounts if we increase the temperature. Now, sometimes we can't increase the temperature enough, and so you have to put, there's other factors that can be put into play, such as pressure, or those are the two most common. But we can manipulate things to try to encourage a reaction to, or by adding a catalyst, we can manipulate things to try to make a reaction occur. But as far as colliding with the correct orientation, we have absolutely no correct control over that, except by making sure that we provide lots of opportunity. I'm sorry, I thought I could go over energy of activation. It just, I'm seeing dead faces, and therefore nothing's gonna land if I don't stop. And also my throat's getting there. I do. So hopefully you got integrated rate laws though. And those aren't so bad. They're just a matter of following a graph and following what y equals mx plus b means. Okay, I will see you tomorrow. As far as I know, I'll be here. As long as I don't have a relapse.